Pyridoxal phosphate, the active form of vitamin B6, is a coenzyme in a variety of enzymatic reactions. The Enzyme Commission has catalogued more than 140 PLP-dependent activities, corresponding to 4% of all classified activities. The versatility of PLP arises from its ability to covalently bind the substrate, and then to act as an electrophilic catalyst, thereby stabilizing different types of carbanionic reaction intermediates. Etymology. PLP stands for pyridoxal 5-phosphate and PMP stands for pyridoxamine 5-phosphate. Consequently, the L in PLP does not indicate a levorotatory chiral center. The common names pyridoxamine, pyroxidal and pyridoxine derive from pyridine plus oxy plus an iupac suffix. Pyridine, in turn, comes from the Greek iuroa, iuroi plus ide plus ime. It should be noted that the oxy infix in pyridoxine is not based on Hansa-Euro-Widman nomenclature and the pi root does not indicate it to be a dimeric acid anhydride. Role as a coenzyme, PLP acts as a coenzyme in all transamination reactions, and in certain decarboxylation, deamination, and racemization reactions of amino acids. The aldehyde group of PLP forms a Schiff-base linkage with the I-micron amino group of a specific lysine group of the aminotransferase enzyme. The I plus or minus amino group of the amino acid substrate displaces the I-micron amino group of the active site lysine residue in a process known as transaldemination. The resulting external aldermin can lose a proton, carbon dioxide, or an amino acid CIDA chain to become a quinoid intermediate, which in turn can act as a nucleophile in several reaction pathways. In transamination, after deprotonation the quinoid intermediate accepts a proton at a different position to become a ketamine. The resulting ketamine is hydrolyzed so that the amino group remains on the complex. In addition, PLP is used by aminotransferases that act upon unusual sugars such as pyrosamine and isosamine. In these reactions, the PLP reacts with glutamate, which transfers its alpha amino group to PLP to make pyridoxamine phosphate. PMP then transfers its nitrogen to the sugar, making an amino sugar. PLP is also involved in various beta-elimination reactions such as the reactions carried out by serine dehydratase and GDP4-keto-6-deoxymannose 3 dehydratase. It is also active in the condensation reaction in heme synthesis. PLP plays a role in the conversion of levodopa into dopamine, facilitates the conversion of the excitatory neurotransmitter glutamate to the inhibitory neurotransmitter GABA, and allows SAM to be decarboxylated to form propylamine, which is a precursor to polyamines. Non-classical examples of PLP is also found on glycogen phosphorylase in the liver, where it is used to break down glycogen and glycogenolysis when glucagon or epinephrine signals it to do so. However, this enzyme does not exploit the reactive aldehyde group, but instead utilizes the phosphate group on PLP to perform its reaction. Although the vast majority of PLP-dependent enzymes form an internal aldermin with PLP via an active site lysine residue, some PLP-dependent enzymes do not have this lysine residue, but instead have a histidine in the active site. In such a case, the histidine cannot form the internal aldermin, and, therefore, the cofactor does not become covalently tethered to the enzyme. GDP4-keto-6-deoxymannose 3 dehydratase is an example of such an enzyme. Catalytic mechanism. The pyridoxal 5-Euro-squared phosphate-dependent enzymes catalyze myriad biochemical reactions. Although the scope of PLP-catalyzed reactions appears to be immensely diverse, there is a simple unifying principle: in the resting state, the cofactor is covalently bonded to the amino group of an active site lysine, forming an internal aldermin. Once the amino substrate interacts with the active site, a new Schiff base is generated, commonly referred to as the external aldermin. After this step, the mechanistic pathway for each PLP-catalyzed reaction diverges. Density functional methods have been applied to investigate the transamination reaction, and the results have shown that the reaction involves 3 sequential steps: formation of a tetrahedral intermediate with the active site lysine and the amino substrate bonded to the PLP cofactor. non-direct proton transfer between the amino substrate and the lysine residue, and formation of the external albumin after the dissociation of the lysine residue. The overall reaction is exothermic, the second step being rate limiting, with 12.6 kilocalories per mole for the activation energy. Specificity. Specificity is conferred by the fact that, of the 4 bonds of the alpha carbon of the amino acid albumin state, the bond perpendicular to the pyridine ring will be broken. Consequently, specificity is dictated by how the enzymes bind their substrates. An additional role in specificity is played by the ease of protonation of the pyridine ring nitrogen. PLP enzymes. PLP is retained in the active site not only thanks to the lysine, but also thanks to the interaction of the phosphate group and a phosphate binding pocket, and to a lesser extent thanks to base stacking of the pyridine ring with an overhanging aromatic residue, generally tyrosine. Despite the limited requirements for a PLP binding pocket, PLP enzymes belong to only 5 different families. These families do not correlate well with a particular type of reaction. The 5 families are classified as fold types followed by a Roman numeral. Fold type I, a uroaspartate aminotransferase family; fold type 2, a urotryptophan synthase family; fold type 4, a uro-D amino acid aminotransferase family; fold type 3, a uroalanine racemase family; fold type V, a uroglycogen phosphorylase family. Biosyntheses. From vitamins. Animals are autotrophs for this enzyme cofactor and require it or an intermediate to be supplemented, hence its classification as a vitamin B6, unlike MoCo or CoQ10 for example. PLP is synthesized from pyridoxal by the enzyme pyridoxal kinase, requiring 1 ATP molecule. PLP is metabolized in the liver. Prototrophy. 2 natural pathways for PLP are currently known. One requires deoxyxylulose 5-phosphate, while the other does not, hence they are known as DXP-dependent and DXP-independent. These pathways have been studied extensively in Escherichia coli and Bacillus subtilis, respectively. Despite the disparity in the starting compounds and the different number of steps required, the 2 pathways possess many commonalities. DXP-dependent biosynthesis. The DXP-dependent biosynthetic route requires several steps and a convergence of 2 branches, one producing 3-hydroxy-1-aminoacetone phosphate from erythrose 4-phosphate, while the other producing deoxyxylulose 5-phosphate from glyceraldehyde 3-phosphate and pyruvate. The condensation product of 3-hydroxy-1-aminoacetone phosphate and deoxyxylulose 5-phosphate is pyridoxine 5-phosphate. The condensation is catalyzed by PNP synthase, encoded by PDXJ, which creates PNP. The final enzyme is PNP oxidase, which catalyzes the oxidation of the 4-hydroxyl group to an aldehyde using dioxygen, resulting in hydrogen peroxide. The first branch is catalyzed in E. coli by enzymes encoded by EPD, PDXB, SERC and PDXA. These share mechanistical similarities in homology with the 3 enzymes in serine biosynthesis, SERC, SERB and EM-. However, EPD is a homologue of GAP, which points towards a shared evolutionary origin of the 2 pathways. In several species there are 2 homologues of the E. coli SERC gene, generally one in a SER operon, and the other in a PDX operon, in which case it is called PDXF. A serendipitous pathway was found in an overexpression library that could suppress the autotrophy caused by the deletion of PDXB in E. coli. The serendipitous pathway was very inefficient, but was possible due to the promiscuous activity of various enzymes. It started with 3-phosphorhydroxypyruvate and did not require erythronate 4-phosphate. 3-Philippine pesos was dephosphorylated, resulting in an unstable intermediate that decarboxylates spontaneously to glycaldehyde. Glycaldehyde was condensed with glycine and the phosphorylated product was 4-phosphohydroxy-309, the canonical substrate for 4-PHT dehydrogenase. DXP-independent biosynthesis. The DXP-independent PLP biosynthetic route consists of a step catalyzed by PLP synthase, an enzyme composed of 2 subunits. PDXS catalyzes the condensation of ribulose 5-phosphate, glyceraldehyde 3-phosphate, and ammonia. This latter molecule is produced by PDXT, which catalyzes the production of ammonia from glutamine. PDXS is A8 barrel that forms a dodecamer. Prebiotic synthesis equals the widespread utilization of PLP in central metabolism, especially in amino acid biosynthesis, and its activity in the absence of enzymes, suggests PLP may be a prebiotic compound. In fact, heating NH3 and glycoaldehyde spontaneously forms a variety of pyridines, including pyridoxal. Under certain conditions, PLP is formed from cyanocetylene, diacetylene, carbon monoxide, hydrogen, water, and a phosphoric acid. Inhibitors. Several inhibitors of PLP enzymes are known. One type of inhibitor forms an electrophile with PLP, causing it to irreversibly react with the active site lysine. Acetylenic compounds and vinylic compounds are such inhibitors. A different type of inhibitor inactivates PLP, and such are I+ or -methyl and amino-oxy substrate analogues. Other inhibitors have good leaving groups that nucleophilically attack the PLP, such as chlorolanine, which inhibits a large number of enzymes. Examples of inhibitors: ALP inhibits alanine racemases, but its lack of specificity has prompted further designs of ALR inhibitors. Gabaculin and vigabatrin inhibit GABA aminotransferase, canalin and 5-fluoromethylornithine inhibit ornithine aminotransferase, amino-oxy SAM inhibits ACC synthase. See also, aromatic L-amino acid decarboxylase, ornithine decarboxylase. References. External links: A11HA06,